I feel very privileged that I can come on stage the second time. I hope you're going to be rewarded because I have a lot to say. So my slides are actually quite packed, so may not be. Is this working? The one behind the laptop. Is it behind? Sorry for the hiccup. So, I have to press it many times. Okay. So, actually, I'm really happy that the stage is set for me because of Heiko's and Christian's talk. We really didn't even chat about this, but everything kind of converges together. It's really looking very nice. So, what I'm going to talk to you about today is how certain like research and ideas about peer-to-peer networking and this research can be combined with the blockchain and provide some really killer infrastructure for the next web. So I really think that what we need is certain tools for developers to kind of think of the Ethereum infrastructure as the next web. So what do we need for that? We talked about Swarm before as in the context of serving static files on the one hand with this kind of preferably low latency property, and on the other hand that serving as a kind of backup layer for the other extreme case, like upload and disappear. That's what we call it, when you upload content and you can just get away and come back after a long time and still find your content there. So that was kind of the bandwidth and storage insurance. So I would like to talk about how this view can be extended with further tools that the usual web stack kind of needs. So the take-home message from this talk will be that basically I'm kind of imagining an infrastructure which, there's a few random brands there, so don't get too carried away if you disagree. But it's kind of in a few years from now, maybe these services can be properly used in production. And I would like to introduce 3 more components into this picture that are not exactly production ready. They are mostly like research phase. So apart from this idea, and apart from the 3 more silly acronyms, the take-home message is that not only static data can be served, but we can provide some certain tools for web developers to deal with the remaining problem for real-time web applications, namely dynamic data, dynamic content. So I'm going to approach it from like 3 angles today. One is about internode communication. This relates to things like what Heiko mentioned about the radar network, the infrastructure that will provide the service for the payment channel like type internode communication. And I'm going to mention, if I have time, the multimedia broadcast, like how certain techniques in peer-to-peer communication network research can be applied here. And thirdly, I'm going to talk about database services. So, what is this all about? So, internode communication is basically the question how. So once we have static content, that's all great and fine, but what we are used to these days is personalized content with real-time web applications. So if you go to Facebook, then you obviously see different news feeds if you're logged in and than if I am, and some people in the old generation might not capture this. So when your uncle says that, oh, look at Facebook and go down the page, then obviously they don't capture this dynamic content is extremely important. So the first question is, how do dynamic content gets around? The question is like very simple. It's basically using the same sort of routing algorithms that we use in Swarm. That's based on the network topology called Kademlia. And sorry, the wrong way. So in Swarm, that we haven't mentioned before, like in detail, that all the files all the documents that you put up, they're basically chunked into little pieces. Whatever file you store, they chunked into 4 kilobyte little pieces, and so you take the series of chunks of a document and hash them. So you take the hash. This hash is going to represent the address that determines where it's stored in the swarm. Now you take the next level, which means that you take X number of chunks, in this case like 128, and consider the hashes, or 128 hashes, as a chunk itself. So the next level, you package them in a separate chunk, and you go further with this story, and you end up with a chunking tree. Now this chunk tree has the following properties. It's got integrity protection, because even with random access, what does that mean? Is that you can basically do range queries in the original content. For example, skip to a part of a movie and still be sure that that particular part or bit in the movie is what you expect from the single hash, the root that you looked up. And that root can be obviously recorded in a system like the Ethereum name service that Nick Johnson of our team will be talking about. What it obviously also allows is to have really compact Merkle proofs of the data, which can serve as the proof of custody for the insurance that I talked about. Now, why is this all interesting? So, if you take this one step further and think about this chunk tree as basically in this simple case, since the branching is 128, you can think of each level as basically a dictionary of ASCII characters. So you can address each chunk in a full document as a series of ASCII characters. So this already suggests that you can think of each file as you can index certain parts with a character string. Now, if you allow these tries not to be balanced and not to have the same depth, then you can basically represent any kind of indexes like that. And that's exactly what Swarm does on the top level, which means that you actually have these manifest files which map URLs to assets, to documents. So in these trees of the manifest, each leaf node represents a document, and each path going to that leaf represents either a URL or say like a path in a directory structure. Now this is nothing new and not very interesting. It's very similar in IPFS, for example. And what's interesting here is that once the file is chopped into these little pieces, then you can use the storage mechanism that we discussed before, like the retrieval and syncing process, to distribute the chunks in a way that's securely retrievable and can be found. Now, if you generalize this kind of mechanism by which this syncing process works and the retrieval process works, then you can see that these are basically general ways to have like point-to-point communication in a network of nodes. So if you combine this general property of how you communicate between nodes and allow storage on top of them, then you can basically cover all kinds of cases of data being pushed around, like push and pull and store or not store. And interestingly, like basically all communications are boiled down to this. I mean, without pretending that I'm going to give you like a full semiotic analysis of all forms of digital communication, but still, it's really that kind of easy in a way. Like you can capture all the known communication medium, like starting from tweets to like Facebook status updates, all the way to email and the chat room. Basically, you can characterize by various properties relating to the internet communication. So along the lines of, for example, who the actual message is meant to be for, whether the message should be delivered or re-delivered if the recipient is not found to be online. So it's the same as like when the postal service like re-delivers your package and just leaves a note, or you can classify them according to their confidentiality, and finally, like all kinds of surface properties, even including how they are displayed in terms of like threaded or timeline. And if you do like these classifications, then you can basically implement using the same node communication. You can implement an entire comprehensive communications infrastructure, and what we already have as a really important ingredients for this is we can use the incentivization the same way that we explained with Swarm. So you can have incentivized communication protocols, and you can use various like APIs, like similar to the Whisper API, where you can address a particular topic, not necessarily like a particular node. In which case you can subscribe to those topics and implement a lot of these interesting communication tools. So let's go one step further. So I'm not going to talk about multimedia live broadcast. This is kind of an interesting topic, and this research into this direction is relatively immature. So I just mentioned that a lot of big companies work around this problem, including Apple, Adobe, and Microsoft, and also like you have frameworks like WebRTC, which all trying to solve the problem that mostly the problem that they're trying to solve are solved by peer-to-peer networks themselves. So there's actually interesting ways in which you can efficiently do delay-sensitive live broadcasting of content. This is using the technique that I termed streaming with adaptive transmission channels. So it's basically a combination of multi-bitrate adaptive streaming and a kind of very interesting adaptive multicast routine, which is very efficient in channeling data towards a set of nodes, a set of peers, without duplicating a lot of traffic. So thirdly, it's very important, and this is where I connect to Christian's work. So databases, as I mentioned with the manifests, the higher level structure of Swarm allows an index of arbitrary keys to arbitrary records, basically like a key value store. So if you already smart contracts allow contract storage, but as we know, like on the blockchain, this is both expensive and slow, and you can also use dApps. You use like local storage in a browser for dApps to store some data, but those are private. So there's an interesting solution by which you can use the Swarm manifest structure in a way that allows you to have like database table definitions. And sorry, I have to skip a few slides here. So the manifests are basically used to encode any arbitrary key value store, and the Merkle-Patricia tree that is included in the manifest is making sure that you can make assertions about assertions about like membership in a particular database. And once you have that, and once you have interactive verification of code, then you have an incredibly powerful system whereby you can secure these database tables by verifiable operations. So, for example, if you have SQL query resolver on top of these manifest encoded database tables, then you can have you can have contracts which check for certain properties of for example, they check the validity of certain indexes or validity of whether a response to a query is actually correct or not, and therefore you can have a computational market which complements this system by providing scalable database retrieval. And so I conclude this by saying that the takeaway message from today is that there is research in like these three areas, and these are three projects that we would like to complete in the next year or so. And these are all basic infrastructure, like base layer infrastructure projects, which are very unlikely to be funded by industry. If we ever get it done, then it's thanks to the foundation that will provide this, the funding for this. So thank you very much.
Thank you, Viktor. Thank you.